Hello everyone, I'm Ronodip. I'll talk about MonkeyDB. It is a database to effectively test the correctness of distributed applications against weak isolation levels in databases. This is a joint work with Deeptangshu Jyoti Akash from Microsoft Research and Konstantin from University of Prague, who was also my PhD supervisor at that time. For the context of this talk, let's look at one example of a bank payment applications. This, uh, this is a basic version of a bank payment transaction to execute a payment from an account balance. Let's think of a situation where someone is trying to pay for an item online. Now imagine meanwhile another payment is triggered in parallel, maybe because of monthly payment or at some online service. If the reads from both procedure calls succeed before one update, then one of the updates will be lost. This is because of the typical race condition. This is because this is called double spending because of the same currency spent twice. Now, to avoid this, the bank database should guarantee something, that the uncommitted effects of these two procedural calls should not interfere with each other. As in, they should be executed in some kind of isolation from each other until they are finished. We say that each procedural call is executed in a transaction. Each transaction is protected by a certain isolation level. A classic isolation level is serializability, where all transactions are executed serially one after another without interference. When a transaction is being executed, others must wait. But executing all transactions serially requires heavy synchronization. There exists a different isolation level called snapshot isolation, which allows some transactions to be executed concurrently, yet offers enough guarantees to run the example bank payment application correctly. Since not all transactions need to run serially, snapshot isolation level provides better performance than serializability. Since snapshot isolation allows some behaviors compared to allowed more behaviors compared to serializability, we say that it is weaker and more permissive than serializability. In general, databases support a range of isolation levels that correspond to different trade-offs between performance and guarantees. Each isolation level allows some amount of interference between transactions. Less interference meaning stricter guarantees, which translate to some amount of synchronization. Less synchronization meaning better performance. But choosing a weaker isolation level for the sake of performance is not always a solution. Ideally, the weakest isolation level have the best performance, but they also allow the most interference between transactions. So choosing a weaker isolation level will probably allow an application to run incorrectly. For example, a weaker isolation level read committed will introduce the race condition in the previous bank payment application, allowing the double spending at someone's account as we discussed before. Finding the sweet spot between performance and guarantees is the key to a correct and performant distributed application. So for a choice of an isolation level, the question we address is in this work is how to check distributed service running under it. So now the straightforward solution is testing, but how do you do it? The popular approach is to run the test against the application using a database configured with the isolation level in question. One issue in doing so is that production databases do not provide coverage for special corner cases which make the test fail. In detail, when using a production databases, one usually needs a huge workload and network manipulation to stretch the database to produce non-serializable behaviors. Otherwise, it is very rare to hit the corner cases which expose the bugs due to weak isolation levels. Also, if a bug is found, it is difficult to find the source as the final log is too big. Again, different databases use different implementation for this isolation level, so different database may produce different behaviors for the same workload under the same isolation level. Due to these shortcomings of production databases, we wanted a better testing technique, which uses a small workload, zero ad hoc manipulation, and only relies on the database runtime. Yet it generates possible behaviors under an isolation level with good coverage to expose the corner cases to hit the real test failures. We present MonkeyDB, which addresses exactly that. It provides reference implementation of database isolation levels based on the axiomatic models. It produces good coverage on small workloads and effectively perform a small test. It has two interfaces, key value and SQL, SQL interface is a drop-in replacement for MySQL Server. Moreover, it does not require any network manipulation. The coverage depends only on its runtime. Later, we show the evaluations to demonstrate MonkeyDB state coverage and effectiveness in testing. Now we talk about the key value interface. This is the backbone of the whole MonkeyDB. So let's go over it using an example. The main idea of to model key value database is to maintain an in-memory log of reads and writes happening throughout an execution. We use axiomatic models of isolation levels to on these logs to maintain the valid ones. In this key value store, each operation comes in sequence. To produce weaker behaviors, we allow reads to return non-return values. The write operations get added to the log as it is, as its view doesn't really depend on the isolation level. Now the read operations are a bit tricky, as the possible return values depend on a particular isolation level. So we enumerate over all possible values for a return, and then check the possible new logs that are valid. After that, we collect the logs that are valid, and then choose a log randomly, and return the corresponding value for that read, and maintain the log for the next operations. Since this requires calling the isolation level checker multiple times at each read, we put significant effort to optimize the procedures for performance. Like we prune the read values that are known to be invalid. We use incremental checker to avoid repeated computations. Now we discuss the SQL interface. The idea is to model the SQL storage with key value and compile the SQL queries to key value queries. Then use the previous key values database implementation to achieve the weaker isolation behaviors. We treat each cell of an SQL table as a key and a value in the key value database. So if we have a SQL table student with two columns, ID and name, in the backend key value storage, they will get mapped by a key uniquely identifying the cell using the table name, column name, and ID, and the value stored at that cell. Similarly, when a SQL query is needed to be processed, the SQL query can be compiled to a set of key value database queries, fetching the data from the key value storage and returning them accordingly, tapping in a proper SQL format. Now I will describe the evaluation of our implementation of MonkeyDB. The goal of the evaluation is to show the MonkeyDB enumerates a diverse set of behaviors within a reasonable number of iterations and small workloads. The first experiment uses a number of microbenchmarks where we can accurately compute the number of possible behaviors and evaluates the coverage we get using MonkeyDB's exploration. We run the experiments on 4 microbenchmarks: Twitter, shopping cart, courseware, and driver stack using the key value API. As an example, I will discuss a plot showing the results we got with the shopping cart example. This is an implementation of a shopping cart for an online shopping application. The x-axis represents the number of times we executed the shopping cart with MonkeyDB, and the y-axis gives the number of unique behaviors observed from those executions within x iterations. For serializability, it reaches the total coverage in 50 runs. For causal isolation, it covers almost all behaviors within 3000 iterations, introducing some delay between queries. This supports the fact MonkeyDB effectively explores all possible behaviors under an isolation level within a reasonable number of iterations. Here we put our implementation to a real test, pun intended. We use a popular SQL database benchmark framework OLTPBench and try to evaluate MonkeyDB on its benchmarks. These benchmarks implement different types of distributed applications. TBCC implements an online warehouse or a tracking application. Small bank implements a small version of a bank application supporting payments between accounts. Voter implements a voting applications to count votes for some candidates. Wikipedia implements a small version of Wikipedia to track the read and updates to its text data. These experiments are done in 3 steps. First, we plug the MonkeyDB into these SQL applications and load the initialization data. Second, we run a non-deterministic workload on the application. Last, we run some SQL queries asserting invariance for the SQL data. The practicality of MonkeyDB is the OLTPBenchmarks can run on MonkeyDB as the MonkeyDB itself is a drop-in replacement of SQL Server. Let's look at the TBCC evaluation. We had 12 assertions to check for this benchmark. The benchmark is supposed to run correctly when run under standard isolation. So we run it under 2 weaker isolation levels, causals and read committed, and try to check how quickly they violate the assertions. Causal is an isolation levels between the weaker read committed and the stronger snapshot isolation. In the plot, the x-axis denotes each assertions from 1 to 12. Blue and orange color denotes 2 or 3 sessions in the workload. The y-axis denotes the percentage of assertions violations. As we can see, like the MonkeyDB runtime is able to violate all assertions with good probability in read committed and many of the assertions in causal. Running the same experiment on MySQL under read committed, we were only able to see violations for 6 assertions, even with 10 sessions and a much larger workload. Next, I'll briefly mention some related work. Jepsen is a quite popular tool in the domain of distributed application testing, but it requires a big workload and ad hoc fault injections to force weak behaviors. Another similar project is Clotho, which tries to statically analyze the distributed applications with a given isolation level and produce a trace using a SMT solver. And they're relying on the axiomatic models. And then replay the trace on a real database. This requires a query scheduler to manipulate the calls to SQL Server and inject faults. With MonkeyDB, the developer can write small tests and forget about ad hoc manipulation. The MonkeyDB runtime is enough to correctly enumerate possible weak behaviors. Now we are almost done. To conclude, I present the contribution slide again. We have presented MonkeyDB, which offers a generic implementation to database for database isolation levels. It enables to test key value and SQL applications, effectively only relying on the runtime without any complicated setup. Now to talk about future work. Right now the MonkeyDB runtime supports one isolation levels at a time. Modern databases support different isolation levels for different transactions in the same runtime. It would be nice to bring the same support to MonkeyDB. The next one is to generate assertions for applications running under an isolation level. Sometimes the production database implement a weaker version of the isolation levels due to some human error or literature description of the isolation level. So running this test against the database of choice will make sure the choice is correct. Another one would be finding the weakest isolation level for an application for which it runs correctly with maximum performance. That way the developers can select and perform an isolation levels without worrying about the bugs due to the weak behaviors. With this, I end my talk. Thank you for your attention.